Hello everyone and welcome to our webinar, Improved Signal Integrity Using Impedance Calculated Circuit Boards. First, I would like to introduce the speakers today. Mr. Philip Rabe is a product manager at Würth Elektronik in the product areas HDI and Signal Integrity. He will present the topic to you. My name is Arndt Baer. I am responsible for online services at Würth Elektronik and I will host today's webinar. Before we start, I would like to point out that your microphones or telephones are muted during the webinar. However, you will still have the opportunity to ask questions using the questions area. This screen shows where the questions area is. You find it on the right-hand side screen of your webinar panel. We will try to give you written answers to your questions that you type in there. For this, we have Mr. Stefan Keller here in the background. At the end of the webinar, we will also have a public question and answer session. There we will also answer a few of your questions in public so you can all see the answers. First, I would like to test the question functionality with you now. So please use your question field now to type in where you attend the webinar from. Basically, we were joking about this, not whether you attended from home or from the office, but which country or town. So you can type in your question where you come from now in the field and we will see the answers. Okay, Burnley, England, Denmark, hello, France, Annecy, I hope I pronounced this right, Belgium, Norway, Spain, very international, very European of course, Spain, others. France, Spain, a lot in France and Spain. Okay, so I can see that the function is working and you found the question field. So anytime during the webinar when you have a question, just type it in. You will receive an immediate answer by Mr. Stefan Keller, and some of the questions we will pick up at the end and answer them publicly as well. Okay. So now, straight to the webinar, I will give the microphone to Philip Rabe, and he will talk you through the webinar. Enjoy.
Welcome to today's webinar about the topic Improved Signal Integrity through Impedance-Matched Circuit Boards. Let me give you a short overview about myself. My name is Philip Rabe. I've been working for the past 8 years for the company Würth Elektronik. I'm working in the product management and I'm responsible for the technology groups Signal Integrity and HDI. First of all, I will give you a short overview about the topics of the webinar. At the beginning, I will show how signal integrity works in common with circuit boards and which factors have the biggest influence on the impedance of the tracks on the circuit board. Furthermore, I will inform you about the key material parameters and explain how we bring theory and manufactured circuit board together. Also, I would like to inform you about how we can support you with impedance-defined layer stack-ups and which information we therefore need from you as our customer. Still, we want to talk about the topic HDI in this webinar and how it could work in common with signal integrity. Here we want to show you the advantages the HDI technology can have regarding signal integrity. Last but not least, I will show you something about the topic high-frequency material, especially for circuit boards that have signals running with frequencies above 2.5 GHz. Firstly, we will examine the question why can't signal integrity be ignored on a circuit board. As you all know, the signal is varying on the way from the transmitter to the receiver. As in our case, the circuit board is the transfer medium between the transmitter and the receiver on which the signal passes are lying, the impedance requirements need to be considered both in the design phase and also, of course, in the production of the circuit board. So impedance matching is needed to keep the variations of the signal quality as small as possible. As every circuit board has an ohmic capacitive in inductive proportion, the circuit board cannot be seen as an optimal transfer medium between transmitter and receiver. The reason for this is that there are many different parameters that influence the signal, or better said, the variation of the signals on a circuit board. These factors are the length of the conductor, which in our case is naturally the track, the material parameters like loose factor, dielectric constant, and of course the layer distance between the signal and the reference layers, the reflection due to the plated through holes. With regard to this topic, I will show how HDI technology will reduce or eliminate the reflections. Further still, I will cover the impedance matching regarding the layer stack-up, the track widths and gaps, and show you their interrelationship on the next slides. Another factor is the crosstalk of conductors that are running on signal layers which are lying over each other with no full copper layer in between. And also the noise interference from external sources regarding impedances. Here I also want to show some helpful possibilities that could help to reduce or even eliminate them with the help of the HDI technology, with an example of a complex HDI stack-up. First of all, I want to show which parameters on the circuit boards will have the biggest influence on the impedance of the track on the circuit boards, and which of them need to be considered for the planning of an impedance-defined circuit board. Please watch the microsection picture in the lower right corner as I go through the parameters for a better understanding, as each parameter will appear on the image in turn. One of the biggest influences on the impedance is the track width, called W, which of course has a very important role in the design of a circuit board. The layer distance between the signal layer and the corresponding reference layer has also a very big influence. Furthermore, the copper thickness can't be ignored, even if the influence of the copper thickness is not as significant as the track width and the layer distance. The same goes for the dielectric constant given by the FR4 material. Track width and layer distance can be considered and therefore adapted by the designer or developer in partnership with the producer of the circuit boards. The copper thickness of the layers depends on the base copper of the materials and the galvanic process. To avoid delays and even a complete redesign, we as a circuit board supplier offer you a competent collaboration even before you start designing the circuit board. Let's go on with the materials and engaging mainly with the permittivity and the thickness of the materials. Here we are only looking into the FR4 materials right now. The laminates are always a combination of fiberglass with a relatively high permittivity value and an epoxy resin with a very low permittivity. So the permittivity values of the laminates mainly result from the proportions of resin and glass in the material. Please consider that we are showing the permittivity range of the different prepregs here. This is because we are referring here to the difference between TG135, TG150 and TG170, as the permittivity of the different TG materials is also different. Moreover, we are considering the dielectric losses, which I will explain shortly. Let's take a look on the prepreg type 106 with a thickness of 40 to 50 micron. For this prepreg the ER value is very low, as the resin content here is very high at 70%. For the 1080 prepreg with a thickness of 60 to 70 micron, the resin content is still lower at 60%. That is why the epsilon R values are higher, than the values for the 106 prepreg. Here the epsilon r value is between 3.2 and 3.7 for the different TG values of the materials. Due to the lower resin content in a 2116 prepreg, which has a thickness of 90 to 110 micron, the epsilon r value here is between 3.6 and 3.8. For the thickest prepreg we are using, the 7628, with a thickness of 170 to 190 micron, the epsilon r value is between 4.1 and 4.6. For the cores, it depends on which prepregs are laminated with the copper foils and what the thickness is, as cores consists of different prepreg types laminated with copper foils. Let's examine the epsilon r value a little closer now. Clearly, the real permittivity of the materials, or better said, the single prepregs, always stays the same. But we need to consider that with smaller layer distances, the field strengths of the electromagnetic fields will have an influence on the dielectric losses. Also, the frequency has a small influence on this. So that's why we know that the epsilon r values, which have to be used for the impedance calculations, need to be defined in relation to the layer distances. That's what we call a so-called lossy epsilon r. In this chart, you see the behavior even if the bigger layer distances will be reached with a higher number of the same prepreg type. Let's take a look, for example, on the 1080 prepreg, which has an epsilon r value of 3.2 for TG135 material and 3.5 for the TG150 material that needed to be used for the calculations. But if you put two prepregs over each other, you still need to use epsilon r values of 3.6, respectively 3.5, to balance the losses due to the bigger layer distance. By using three prepregs over each other, from this type of prepreg, the epsilon r value that need to be used for the calculations are 3.6 or 3.9. For the other thicker prepregs like 2116, for example, the effect is still the same, as you can see here. As you can see here on the next chart, we have more or less the same behavior on the cores, but in some cases this effect can be a little smaller depending on the kind of prepreg that is used in the cores, as sometimes maybe a thicker core has prepregs inside with a higher resin content than a thinner core. You can see this effect here in the difference of the permittivity of the 150 micron core and the 250 micron core. So the epsilon r values we are using for the calculations we call effective epsilon r values. Now maybe you are asking yourself the question, how could we determine these exact values? First of all, we need to say that the values we use are average values. We determined through many measurements, microsections, and the corresponding calculations. So in this case, we come to the point how the epsilon r values are defined through the extrapolation of these values with the help of the microsection results. In our case, we use the Polar software for these kind of calculations. The determination of the epsilon r values can be done with a so-called backwards calculation. Please now also take a look at the microsection picture and the picture of the software tool below, as the values will be marked when I mention them. First of all, we need the value h1, the layer distance between the signal and the corresponding reference layer. In our example, the outer layer and the first inner layer. W1, the lower track width. W2, the upper track width at the head of the track, which is always smaller than the lower track value due to the production process. But please note that this value is still defined in relation to the copper thickness. T1, the copper thickness, you can also say the height of the track. C1, the height of the solder resists on the substrate beside and between the tracks. C2, the height of the solder resist on the track. and of course the epsilon R value of the solder resist itself. By having these values, you can define by calculation with the software the permittivity of the cores and prepregs. Regarding the layer distances, it needs to be considered that the pressed thicknesses of the prepregs do not always have the same thickness depending on the kind of layers they are placed in between. Here there are still differences due to the fact that they are, for example, between signal layers or maybe between planes. If we take a look on the configuration between a signal layer and the plane layer, and 1080 for example, is about 65 micron thick if both layers have 17 micron copper thickness. Between 35 micron copper thickness it is still 60 micron thick. If two 1080 prepregs are used, the thickness is 134 micron at 17 micron copper and 128 micron for 35 micron copper thickness. Between layout against layout, two 1080 prepregs between two 17 micron copper layers are 128 micron, and between 35 micron copper still only 120 micron thick. By taking a look on the last configuration, plane against plane, one 1080 is 70 micron thick between two layers with 17 micron copper thickness and 68 micron between 35 micron copper thickness. Two 1080 in this case have 140 and 136 micron. Please note that these thicknesses are values we determined for our processes. Let's come now to the general topic, impedance calculation and service we can offer you as our customer. We can do both. We can create an impedance-defined stack-up for you, and we can recalculate yours, maybe correct it, or offer you an alternative solution. We at Würth Elektronik are able to calculate all common impedance configurations. Surface microstrip, which means that there are impedance-defined tracks on the outer layer with a reference on one of the first inner layers. Embedded microstrips, which means that there are impedance-defined tracks on an inner layer with a reference on one of the lower layers, but no reference on the layers above and the outer layer. And of course stripline configurations, which means that there are impedance-defined tracks on the inner layers embedded between reference layers. Even every existing line configurations model we can calculate. Normal single-ended tracks, for example 50 ohm, as a very common value, and differential track pairs, like for example 90 ohm USB or 100 ohm. We can also calculate coplanar structures, which means that the single-ended track or the differential track pair is embedded between ground areas on the same layer. Here it is important to consider that this ground area has to be at a constant distance to the impedance-defined structures over the whole length of the structures on both sides. This distance should be relatively small. Before we go on now, we have prepared a small poll for you. We want to know from you which parameters on the circuit board have the biggest influence on impedance. For the poll, I want to give over the microphone to my colleague Arndt.
Thank you, Philip. So now here's the question: which parameters have the biggest influence on the impedance of a track? And right now I will start the poll. You will see a multiple choice, in fact single choice question, and you can click on this and choose one of the possibilities that's most likely for you. So we have as an answer copper thickness and solder resist, track width and layer distance and copper thickness. So what do you think? Click on the solution you think is most likeliest. See, okay, the answers are pouring in. 38% have already answered. We have now reached the 50% contribution mark. 58%, so I'm waiting a bit more till a few more people have answered it. Okay, we're coming close to the 100. Well, actually, we're at 75% now, so yes, we have reached the 75% now. So I think since no more answers are pouring in, I will now close the poll and I will show you the answers. That's how you have answered it. So 78% of all participants have voted for track width and layer distance, which I can already tell you is right. Copper thickness and solder resist was 6%, and layer distance, as you can see, and copper thickness are 17%. And I'm handing over back to Philip so he can give you a bit more information about this, of course, and to continue with the presentation.
Thank you for participating on this poll. For sure, the answer is track width and layer distance, as the most of you also choose. The other parameters do also have an influence that can't be ignored, but track width and layer distance still have the biggest influence on impedance. So then we can close this poll and go on with the webinar. For our calculations to create a stackup or just checking customer stackups, we consider every parameter that is possible with the calculation software. On one hand, the parameters we work with are constant values. The dielectric constant of the FR4 material from our determined values for each core, prepreg, and the most common prepreg combinations, the dielectric constant of the solder resist, and the different thicknesses on, between, and beside the tracks. The upper track width, which we define according to the copper thickness. For 35 micron copper thickness, for example, we use the difference from 20 micron from the lower to higher track width. And for the standard copper thickness on the outer layers of about 45 to 55 micron, we use a difference of 30 to 35 micron. And of course the parameters that can be changed or adapted to reach the target impedances, like lower track width and gaps that can be changed in the layout if possible, the layer distance, and the copper thickness. In order to create an impedance defined stackup for you as customer, some information is needed. It has to be clear what type of stackup it is. Is it a standard multilayer or maybe an HDI stackup, for which we need to use wire types as for HDI stackups to the order core and prepreg can be different compared to a normal multilayer, especially if we have more than one pressing process. Then of course the number of layers, the overall thickness of the PCB, the desired copper thickness, especially the base copper thickness on the inner layers, the layer order, that means the position of the signal layers and the corresponding reference layers, of course your required impedance values, and if possible the desired track widths and gaps you want to use. Here it is also possible to give a range of values like maximum or minimum track and gap values. By having all these values, we are able to create a possible stackup for you, with advice what layer distances, track widths, and gaps you can use to reach the needed impedance values. Here we want to show you some standards. Moreover, you can see here the reason why we qualified the 2113 prepreg beginning 2012. The reason was that for example, the 1080 prepreg is often too thin to reach the desired track widths for 50 ohm, but particularly for 100 ohm differential requirements. For 100 ohm, it would need a very big gap if you want to stay at 100 micron track width or bigger. On the other hand, a 2116 prepreg is in many cases too thick to reach structures that can place easily in your layout, and on the most cases you do not have a lot of space on the circuit board. This is, you can see, especially for 50 ohm value, where the track width of 180 micron is needed to reach 50 ohm. With the 2113 prepreg, the track and gap values are more or less exactly in between the values for the other prepregs, so it offers more options for impedance controlled design on outer layer but also on inner layers. Furthermore, it is also possible to realize laser drilled microwires with these prepreg. Here you can see an example how such a stackup we can create for you can look like. On these pictures you can find all important information like type of the stackup, layer distances, type of cores and prepregs and the corresponding dielectric constant values, layer order and copper thicknesses. Furthermore, you can find the possible track widths and gaps that are needed to reach the needed impedance values. If we checked your defined stackup and values, we give information what impedance values can be reached with your track and gap values and how they need to be changed to reach the desired impedance values. Impedance measuring is also possible for us. To measure the impedances, we use a tool from Polar. The measurement method is the TDR, which means that the reflections are measured. With the help of such test adapters, we can measure single-ended impedance values and also differential line pairs. The result has to inside the tolerances over a defined section of measurement. This area you can see on the picture inside the red marked area. The curves you can see at the beginning and at the end results from the transition between the PCB and the test adapter. But to measure impedances, we need to use test coupons, as it is not possible to test directly on the board, and it would also be not exact enough. In general, we have two different types of test coupons. One for single-ended structures, where we can bring in 6 test structures, and one for differential tracks, where we can bring in 2 different test structures. On these test coupons, we can realize more or less the same circumstances as on the circuit board itself, regarding position of the signal and reference layers and also the copper that is existing on the layers the signal are running to have the same layer distances that are also existing in the layout. The test coupons are really needed to make sure that the connection of the test adapter is correct to measure the impedance values, like pad size and wire diameter. And also it is important as the test coupons are designed according to a defined measuring length. The test coupons are placed in each production panel then for the production. So they have to be considered for the panelization, as normally we try to place them somewhere on the panel so that the number of circuit boards we can place on the panel is not affected. But depending on the size of the circuit boards and the number of test coupons that are needed, it can be possible that less boards can be placed on the panel. On the basis of the measurements, a test report will be generated. These test reports include several details like customer and job information, the input impedance values on which layers have been measured, and of course the results of the measurements. The smallest tolerance on impedances we can offer is ±10%. In the end, we send the boards and the test report to the customer. Before we go on now, we have prepared a small poll for you again. We want to know from you, why did Würth Elektronik qualify the prepreg type 2113? For this poll, I want to give over the microphone again to my colleague Arndt.
Okay. Thank you, Philip. Okay, so here you see the question again. Why did Würth Elektronik qualify the prepreg type 21113? So I'm doing the live poll now. You should see it now on your screens, and as you've seen before in the previous poll, you can now start to vote. 1 vote each, and I see the votes already coming in. Actually, one person has already voted, so please feel free to vote. Okay, so we have 50% of participants have already voted. It's still coming in, so we wait a few more seconds. Okay. Thank you very much. And okay, now we have reached the 75% participation. Actually, more than we had in the first poll. So 86% of all people have now voted. So I don't think there's much more coming in. So I'm closing the poll now. Thanks very much. And here are the results. As you can see, which is quite surprising for me that it's not as clear as it was before. 72% of all people say to have more possibilities for impedances. The second option, because it is cheaper, nobody voted for, but the first one has really 28%. So let's see what's right and actually try to get an answer on why it's right from Philip. So I'm closing the poll again and over to you, Philip.
Thank you for participating on this poll. The correct answer, as 72% of you also quoted or choose the option, is that we have more possibilities for impedance requirements, especially on the outer layers. So we close this poll and go on with the presentation. Let's stop the part of impedance measurement and go over to the HDI technology in association with signal integrity. On the left picture you can see a simple drawing of a signal path in a circuit board, which has been realized with normal plated through holes. Marked in red you can see the more or less needless part of the wire in the signal path, which of course has still influence on the impedance due to the reflections. These areas are so-called open-end antennas. On the right picture you can see now the same signal path realized on the circuit board with the help of microwires and buried wires. And as you can see now, we have direct signal paths without reflections due to the plated through holes. These signal paths can be realized with the help of microwires, staggered or stacked microwires, or with a combination of microwires and buried wires. So as you can see, blind wires and buried wires results in reduced discontinuities. Furthermore, some interesting information about EMC problems on the circuit board due to the external sources. On this picture you can see a board with an excellent EMC shielding, as here there are no signals running on the outer layers. The routing of the components, especially the BGA, in this case realized with wire and pad technology, as you can see on the picture. Because of this, it is possible to work with more or less complete copper area on the outer layers. The signals on the inner layers are therefore very well protected from external sources. Let's take a detailed look on the breakout of the BGA to see the solution with HDI technology. In this cutout picture from the BGA you can see the laser drilled wires in the pad. Now you can see a 3D graphic of this area and the staggered microwires from layer 1 to 2 and 2 to 3 to adapt the signal layers. As you can see now in the section picture, the signal layers 2 and 3 can be easily reached with the microwires, so a direct signal way can be realized. In the micro section you can see now how this looks like in the circuit board. Next you see the solution microwires combined with buried wires. In the section picture you can see that even with the combination all further inner signal layers can be reached, even as the bottom layer. As you can see here, microwires can be placed beside the buried wires, or as shown on this microsection picture, it is also possible to put the microwires directly on the buried wires to reach all other signal layers. A design suggestion from our side: if you still need buried wires in the circuit board, you should try to replace as many plated through holes as possible with the combination of microwires and buried wires, as even for the signal path it is very helpful if you remember the reflection due to the plated through holes. Here is now an example stack-up for such a solution. If you take a look at the signal layers, you can see that it was a target to work more or less with the same layer distances above and below the signal layers, up and down to the next reference layers. Like this, it is possible to work with the same track width on both layers, in this case 100 micron width with track distance of 240 and 152 micron for 100 ohm differential and 100 micron layer if 100 micron layer distances is used. On inner layers without microwires, it is also possible to work exactly with the same track and gap values for the impedance-defined structures by using a symmetrical stack-up. But that's what we do. FF4 stack-ups always need to be symmetrical. Here you can see the BGA of an inter-at-home processor as an example of a complex 0.6 mm BGA which can be routed with the help of microwires. The BGA breakout can be done in this case without any constraint on impedances. Due to the possible pad sizes for the microwires in such a BGA, we can still work with 100 micron layer distances. In this case, even 100 ohm are possible by routing with 90 micron track width. But please note that 0.6 mm is the smallest BGA where this is still possible. For smaller BGA pitches like 0.5 mm or 0.4 mm, this is not possible, as here, due to the maximum possible wire pad sizes, only layer distances of maximum 60 to 70 micron are possible. For such a small BGAs, smaller track widths need to be used, or the needed structures have to be placed on layers with bigger distances to the next layers. Let's summarize the topic. HDI technology is ground on the outer layers. To use the outer layers as a ground offers and also needs direct contact of the solder pads with the first and second inner layer with the help of staggered or stacked microwires or the combination of microwires and buried wires. With an optimized XY routing, you can reduce the crosstalk between the signal layers that are placed above each other. Big advantage is that due to the fact that outer layer is ground, you have a very good EMC shielding from external sources. Using 100 micron layer distances on the microwire layers offers you the option to place all impedance-defined structures, for example 100 ohm, nearly without any constrictions. A very common material on the market, if we take a look on the high-frequency material, is for example the Rogers material 4350B with frequencies of 77 GHz can be reached. But such high frequencies are normally only used for radar and radio applications, and it is still very expensive. Taking a look at the material costs of the different types of the materials. If we say that, for example, our standard FF4 TG135 material is 100%, which you can see here in purple color, then you can see that the costs for the TG150 and the TG170 materials is still a little higher. The yellow and blue bars show the price of high frequency materials that work up to frequencies of 10 GHz or 15 GHz. We call such materials also mid-performance materials. The last green bar show the price of such high-performance materials like Rogers, which are compared to the FF4 materials 8 to 13 times more expensive. So you can imagine that this is a very high influence on the price of the PCB. In the most cases, such materials are not needed, as many applications need only frequencies up to 10 GHz. Due to the fact of the material prices, we are looking right now for so-called mid-performance materials to be able to offer you something for the most applications. So our further activities in these technologies are to look for project partners that are looking exactly for materials like this for their requirements. These will be materials that can work in frequency areas of 2.5 GHz up to 10 or 15 GHz. Furthermore, these materials have to be established in the production and the processes have to be defined. The big advantage is the much lower material costs when compared to the high performance material. Materials we are thinking about are, for example, EMC Elite EM888, Isola FR408HR, or the Panasonic materials Mectron 2 and Mectron 6. So if you are interested in making such a project with us, please contact us. Now we come to the end of the webinar. Please keep in mind that higher transmission rates and frequency increasingly more often needed matched impedances. For this fact, we can offer you a very competent service, as you know. For higher transmission rates, high frequency materials can also be necessary. To comply with the needs of the market, also price sensitive high frequency materials are needed. So we are prepared for it. So in this case, thank you very much for your attention. I really hope you enjoyed the webinar and that you were able to gain some new perceptions. Furthermore, we would like to welcome you for one of our webinars in the future. Subsequently, we will try to respond to all of your questions you asked during the webinar. Due to the high number of questions, we haven't been able to answer all of them immediately, but we will follow up and send you an answer during the next days. Also, we will publish an FAQ on our homepage where the most frequently asked questions and the corresponding answers will be listed. So here I will give over the microphone again to my colleague Arndt.
So thank you, Philip, for this very interesting presentation. And before we start the question and answer section, I would want to point you towards a survey that will follow up after you have finished this webinar program, and we'd really like to ask you to give us feedback on the webinar. Because that helps us to improve our webinar. It's just a few questions, and that will also prepare us for the next webinar. So there's also a place where you can give suggestions on new topics, on improvements, how the webinars are held, etc., etc. Okay, so now let's move to the question and answer section. We will answer a few sections, but the time does not allow us to answer all of your questions, so we have just picked a few of them. As Philip has said, answers to all your questions will be published on our website under the webinar section, and we will also send out an email after the webinar, a few days after the webinar, with information where you can find this. Okay, so I will ask the first question that came in, and the question is, how big can the maximum gap be between two tracks in a differential pair? And for the answer, of course, I hand back over to Philip.
So thank you for the high number of questions, first of all. So I will repeat the question. The question was, how big can be the maximum gap between two tracks in a differential pair? So the answer is that ideally the maximum gap should be 2 times the track width. but in worst case the gap should not be bigger than 2.5 times the track width. A further question was, why are there restrictions for impedances for an 0.4 mm and an 0.5 mm pitch VGA? The answer is because due to the smaller pads for the microwires we need for such small pitches, the maximum layer distance is 60 to 70 micron, which makes it very difficult to realize especially differential impedance pairs. Another question was, why do the track widths should be ideally 100 micron or bigger for impedance value structures? Here the answer is that because for smaller tracks, tolerances of the etching process in the production have a too big influence on the impedances. Further, one of you asked, do it need to be considered if there's solder resist on the outer layers or not? Here the answer is yes, because the solder resist has a totally different epsilon R value than air. And the last question I will follow up right now due to time reasons is, do we measure the impedances for all boards? Here the answer is no. This we do only if the customer requires it, as we need to count some extra costs for the measurement of the PCBs. Due to the more effort we have, like the creation of the test coupons, the measurement himself, and the creation of the test reports. Due to time reasons, we cannot answer more questions right now. So from my side, I wish you a nice day and say goodbye to you.
Thanks again, Philip. And for me, it's just up to me to finish the webinar. If your question hasn't been answered, or if you have further questions and they will not appear in the FAQ, please do not hesitate to contact Philip. You see his email address on the screen right now. So that's for the Q&A section. And for me, it's now time to point you to the next webinars that we are doing. As you can see on the screen right now, on the 5th of November, we have a webinar about wire-late, the combination of power and control electronics on the circuit board. And with wire-late partial thick copper technology, this is possible. If you didn't know that and want to learn more about this, please subscribe now. And on the 3rd of December, there's a webinar about thermal management, especially in connection to LED applications. So if you're interested in one of them or even both of them, please do not hesitate to register now. The registration is on already under www.weonline.com/pcb-webinar. Okay, so this is about our next webinars. So the last that remains is to thank you for your participation and your time. I hope you got some valuable information and maybe get in contact with our product managers like Philip. And so the last thing is to wish you a nice day, and we hope you enjoyed it. So maybe we see or you listen to us on one of our next webinars. Have a good day. Goodbye.